In this video, we're going over the concepts of Chapter 3, which is titled Chemical Bonds, Molecule Formation. The elements of the periodic table will combine to form either ionic or covalent compounds. Let's now discuss which type of atoms will form ionic versus covalent compounds. Let's focus on the left side of the slide. Ionic compounds form because there is a transfer of electrons. Specifically, what we have is that metal elements will transfer an electron to a non-metal element. In that transfer of electrons, since the metal is losing electrons, it's going to form a positive ion, which means that this is a charged atom. The nonmetal, because it's going to be accepting electrons, will also form a charged atom. In this case, because of accepting a particle that is negatively charged, it's going to form a negative charge ion. When it comes to ionic compounds have an ionic bond. But the ionic bond, as we can see in the diagram, comes from the interaction of a positive charge ion and a negative charge ion. There's no line written in between the two atoms. When it comes to the physical properties for ionic compounds, it includes that they are solids at room temperature. That means that most ionic compounds are known as salts. Additionally, ionic compounds have high melting points and high boiling points. Next, let's go over what kind of elements are going to form covalent compounds. When it comes to covalent compounds, they form by sharing electrons. Typically, we observe that a non-metal element shares electrons with another non-metal element. In addition, a metalloid can share electrons with a non-metal element to also form covalent compounds. When electrons are shared between the two atoms, we can observe that then you put them in between the atoms that are sharing electrons. So we can see that these two elements that are sharing electrons, I'm illustrating and highlighting in green the electrons that are shared. Those shared electrons, it was what forms a covalent bond. Covalent bonds can also be illustrated by connecting the metalloid or nonmetal element to the other nonmetal atom via a line. And then you can write the dots that remained on each atom. And later we're going to see how those are called lone pairs. Let's do a practice problem to identify how likely are certain pairs of atoms at making either ionic compounds or covalent compounds. Specifically here, you can see in the instructions that it is reading which of the following pairs are likely to form ionic compounds. So if they don't form an ionic compound, that means that it's going to make a covalent compound. The first thing that you have to do when it comes to a problem like this is that specifically you are going to identify if the atoms that are here, in other words, the elements, are metal, nonmetals, and metalloids. So in order to practice, I'm going to do specifically problems A, C, and E. Let me classify the elements that are present. First, helium is a nonmetal. Oxygen is a nonmetal. So that means that when it comes to forming an ionic compound, which I'm just going to highlight them in yellow, those two atoms will not form an ionic compound. Next, we have chlorine and bromine. Both of them are non-metal elements, so they also will not form an ionic compound. Lastly, we have sodium and potassium. Sodium is a metal. Potassium is also a metal. So when it comes to this also will not make an ionic compound. Let me show you an example of an ionic compound. On letter B, we have magnesium and chlorine. Magnesium is a metal. Chlorine is a non-metal. So this means that the atoms in letter B will form an ionic compound. I mentioned that when it comes to ionic compounds, one of the things that we observe is that ions are forming, meaning charged species. And when it comes to this, let's take into account that we have words to describe positive charge ions and negative charge ions. On letter A, we observe how sodium, which is a metal element, is going to be forming a positive charge ion. Metals are going to lose one or more valence electrons in order to make this positive charge ions, which we know as cations. And in the case of sodium, we can see illustrated in this diagram that is more similar to the Bohr model, that unpaired electron that we have in the outermost shell, meaning the valence electron, and understand that not all valence electrons are unpaired. It happens to be that in sodium, it is unpaired. Nevertheless, when it comes to sodium, that valence electron, which we can see illustrated here, is going to be lost and it will be transferred in an ionic compound to a nonmetal. As a result, since sodium lost one electron, then it gets a positive one charge. So when that happens, sodium is going to form a cation. More importantly, when it comes to this situation, metal elements lose one or more of their valence electrons to make these cations, because when you specifically look at their electron configurations, then they're going to have electron configurations that are similar to ones that we have in noble gases. You can do the electron configuration for sodium at ground state with 11 electrons versus sodium when it lost an electron. So now it only has 10. And you can demonstrate yourself that when it comes to this, sodium now appears to look like a noble gas. When it comes to non-metal elements gain electrons. We can see, for example, that this is fluorine. Fluorine in its outermost shell is going to have 7 electrons. So it has 7 valence electrons. It's going to gain an electron to now form an outermost shell that has 8 electrons. Since it gained only 1 electron, that's why we see a -1 charge for the fluorine. Additionally, when fluorine or any other nonmetal gains 1 or more electrons, the charge ion that it forms is called an anion. When you do the electron configuration of fluorine at ground state versus fluorine when it gained 1 electron, you will see that similarly to what I just explained with sodium, by gaining that electron, specifically, atoms are going to now have electron configurations that are similar to those of noble gases. Since in general, atoms are going to be losing electrons or gaining electrons to have 8 electrons in its outermost shell, that is known as the octet rule, which by definition, as you can see, this is going to mention how atoms will lose or gain, or at times when we see later, the covalent compounds share sufficient electrons to achieve an outer electron arrangement or configuration identical to that of noble gases. Noble gases are very stable in terms of atoms. So that's why elements wants to achieve an octet when they can. And in the case of ions or ionic compounds, we are going to do it by transferring electrons from metals to nonmetals. Let's now look specifically at ionic compounds. As I mentioned, ionic compounds is going to be a substance that specifically has 2 ions of opposite charge. We need a cation and we need an anion. An ionic bond essentially is not a line that we write between the 2 atoms. Ionic bonds are going to be an electrostatic interaction from the cation and the anion that we have in our ionic compound. So ionic bonds in essence are just an attractive force that holds together the 2 ions of opposite charge. To look at an example, we can see the right side of the slide where we have sodium and chlorine coming together to make a compound that is known as sodium chloride. In specifically this ionic compound, sodium is going to lose 1 electron and is going to transfer it to chlorine. And understand that when that happens, both atoms are going to become charged species. Sodium specifically becomes the cation. Chlorine specifically becomes the anion. But at the end, if we look specifically at both atoms' outermost shells, and you count the electrons that they have in their outermost shells, you will notice that both of them have 8 electrons. When it comes to ionic charges, these can be derived from the group numbers specifically for representative elements. And in representative elements, all of this has been encompassed in the following diagram. Let's first understand how this looks for metals, which forms cations. When it comes to the metals that live in group 1, in other words, in group 1A, lithium, sodium, potassium, rubidium, cesium, all of them are going to lose 1 valence electron to look like their corresponding noble gas. So all those elements in group 1A have a charge of +1. In group 2A, specifically magnesium, calcium, strontium, and barium, we can see that we'll lose 2 valence electrons to make a +2 cation. And you can see towards the left of the diagram, once they lost those 2 valence electrons, which noble gas they will look like. Lastly, when it comes to group 3A, this +3 charge for aluminum also applies to gallium and indium. That means that the atoms, specifically only aluminum, gallium, and indium, will be able to lose 3 valence electrons to become a +3 cation. And we can see on the left side of the slide, what are their corresponding noble gases that, or noble gas configurations in terms of the electrons that they will form. So in general, just know the elements in group 1A form a +1 cation. The elements in 2A, specifically magnesium, calcium, strontium, barium, a +2 charge. The elements in 3A, specifically aluminum, gallium, and indium, a +3 charge. Let's now look at the trend for the non-metal elements. In the case of the non-metal elements, we can observe that in group 5A, the trend only applies to nitrogen and to phosphorus. And those two atoms will form a -3 charge. That means that nitrogen and phosphorus can accept 3 electrons to become specifically these noble gases in terms of their electron configurations. Next, in group 6A, the following applies to oxygen, sulfur, and let me also include selenium. In 6A, those 3 atoms will gain electrons, specifically 2 of them, to have a -2 charge. And lastly, when it comes to the halogens, we see that fluorine, chlorine, bromine, and iodine are going to accept 1 electron in order to achieve electron configurations like noble gases. Remember, all of that is attached to the octet rule. So the charges for the elements in 7A is going to be -1. Make sure that you know and place in your periodic table the information of the charges by group. Now that we know how the charges are developed specifically for representative elements that live in 1A, 2A, 3A, 5A, 6A, 7A, let's learn how to write chemical formulas given ions or given specifically the names of the components for an ionic compound. The basic rules of how to write chemical formulas are given on the left side of the slide. We can see that if you're given specifically names for the elements like we see in the bottom, all we have to do is write the symbol for the metal cation and its charge, write the symbol next for the non-metal anion and its charge. Then we are going to take the value of the charge, make it the subscript of the other ion, and we will see that occasionally we have to reduce the subscript to the smallest whole number ratio, but that is only when necessary. Let me illustrate 2 examples of each of these problems to see how we develop chemical formulas for ionic compounds. If we look at the first part of the problem, it reads, write the correct ionic formula for the compound formed between each of the following pairs of ions. So at this point, the ions have been given to you. You don't have to look at their group in the periodic table. I'm going to do letter A and letter B. So for this first problem, we don't have to follow steps 1 and step 2 because it's already been done. For letter A, then we must do step 3. Let's take the charge value, just the number. So in the case of aluminum, the 3, and we're going to make it the subscript of the chlorine. The chlorine, we can observe that there's just a negative number. There's a value of 1 that is implied but not written. And that value of 1 is the subscript of the aluminum. So when we first proposed for letter A, the chemical formula, we're going to write Al1Cl3. It is known that when you have a subscript of 1, they are always omitted. That's why initially we saw that the number 1 here was not written. So in our chemical formula, we must erase that value of 1. The final answer for the ionic compound formed from aluminum and chlorine is AlCl3. Let's now do letter B. In letter B, we're going to take the 2 of calcium and make it the subscript of the sulfur. We're going to take the 2 in the sulfur and make it the subscript of calcium. So at first, when we write our chemical formula for this compound, we're going to write Ca2S2. In an example like letter B is where we use step 4. We're going to reduce the subscript to the smallest whole number ratio. Since 2 is divisible by 2, we are going to exactly do that. We're going to divide both by 2, which means that the resulting chemical formula is Ca1S1. As I mentioned, a subscript of 1 is always omitted, so we're going to erase those values of 1. So my final answer is CAS. Just as a guideline, when you have atoms in which the cation charge can cancel with the anion charge, by good practice, instead of doing these steps, what you can do, since the cation and the anion will, when added, cancel each other, meaning that if you add those two amounts, it equals 0. In practice, all you have to do is just write the letters of the elements. That is just a shortcut that I want to illustrate. Let's move on to the second problem that we have here in this slide. It reads, let's write the symbols for the ions and the correct chemical formula for the ionic compounds formed by each of the following. When it comes to this, we have to follow steps 1 through 3 and 4 only if necessary. Let's do for the second problem, letter A and letter B. When it comes to letter A, we can observe that we have our metal cation, calcium, which its symbol is capital C and then small a, because that atom lives in group 2A. It has a charge of +2. If you write it as 2 plus, that's okay also. Then we have chlorine. Chlorine, its symbol is Cl, and its charge, because it lives in group 7A, is -1. Next, we are going to take specifically the value, meaning the 2, and that's becoming the subscript of the chlorine. We take the value of 1, and that becomes the subscript of the calcium. Our final answer here at first looks like Ca1Cl2, and as I mentioned, subscripts of 1 are always omitted. So our final answer for the ionic compound that forms from calcium and chlorine is CaCl2. Let's now do problem B, where we have the ionic compound that comes from rubidium and bromine. In letter B, we are going to write the symbol for rubidium, which is Rb. And rubidium lives in group 1A of the periodic table, so it has a charge of +1. Bromine is an element that its symbol is Br, and it has a charge of -1 because it lives in group 7A. You can observe here that if I add +1 and -1, that will equal 0. Since that +1 and minus charge when added will equal 0, then my final answer, I don't even have to crisscross. All I have to do is to write the symbols for the element. So the ionic compound that forms from combining rubidium and bromine is RbBr.